Fault! No, we're not at the US Open or Wimbledon, and we're not here to talk about anybody's personal faults. We're here to explore the world's most famous geological fault and plate tectonic boundary. We're here in California to take a tour of the San Andreas Fault. So we have a few stops for you. Let's go.
The San Andreas Fault is a source of some of California's most significant earthquakes, including the horrific 1906 disaster and a lesser well-known one in 1857, the Fort Tejon earthquake, which was one of the strongest earthquakes, estimated to be about an 8 on the Richter scale. But because the quake was in such a remote location and California was not heavily populated yet, there was little damage and almost no casualties and very little press about it. But today, in the 21st century, the same quake at the same magnitude would be quite a different story. The San Andreas Fault is the boundary between the Pacific and North American tectonic plates. It stretches nearly 700 miles through California, from the Gulf of California in Baja, Mexico, to just south of San Francisco, where it goes into the ocean and then reemerges on land shortly before heading out into the ocean near Cape Mendocino, California. It is known as a strike-slip fault, and it is a transform boundary. So while it may be a transform boundary, the type of fault that the San Andreas is a strike-slip fault or a lateral slip fault. It's moving horizontally, and the North American and Pacific plates slide laterally against each other. Now, the San Andreas Fault is broken into several segments, and overall, the San Andreas is moving 2 to 3 centimeters a year, but some segments of the San Andreas are much more active and busy than others, which appear to be quiet and locked, and that's generally not good for a fault to be locked. We're going to start at the southern end where the San Andreas enters land and from the Gulf of California, and we're going to move slightly to the northwest at the Salton Sea, which was a low flat area created not just by the lateral shift of the San Andreas, but also because the fault starts making this left or northwest turn. And so it creates not just a low area, but there's actually a little rifting or pulling apart. And that's why this area is kind of a little topographically lower than the surrounding area. And what's also interesting in this area is that there's geothermal activity in this in the Salton Sea. There's actually around this area and in the sea, there's local geysers and mud pots in and around the Salton Sea area. It only got this large through irrigation and canals and ended up getting flooded by the nearby Colorado River. And ultimately, it created this very saline lake. It has no outflow to the ocean, and so it remains very salty. Not as salty as the Great Salt Lake in Utah, but very salty. And this artificially created kind of an environmental disaster, but that's another conversation for another day. But it sits right on the San Andreas Fault. There are earthquake swarms in this area within the Salton Sea area, and there is that geothermal activity to indicate not just lateral movement, but kind of a little rifting to allow magma to come up. And so a lot of geologists think that this area will become inundated all the way to the Gulf of California and will become connected. It will be a much larger lake area and perhaps even continue as a divergent plate boundary. So the next area we're going to fly to is in the Carrizo Plain, and this vast expanse of dry, open desert and low grassland may be the best visualization of this intersection of the North American and Pacific plates. And it was in this section of the San Andreas in 1857 that there was a 30-foot, 10-meter shift along this plate boundary, which tells you just how much stress and energy was built up and released. The San Andreas Fault is sometimes very subtle and sometimes looking like a long linear scar cutting through the landscape. It may be a narrow valley with ridges on both sides, kind of a slight crumpling from the slower movement along the two plates. But because we can see streams that are trying to cross and how they are offset in one direction. And one of the most famous places we can see that is called Wallace Creek. It's now a dried up stream. And nearly 1,000 years ago, the stream actually crossed the fault as a straight line. But as the Pacific plate slipped over time, it caused the direction of the stream to change. And now there's over 100 meters of offset along the fault. And you can see that here, where the stream on the North American side, and then there's this 100-meter shift to the north, and then the stream continues, the dry stream bed continues on the other side, the western side, which is the Pacific plate. So the stream has adapted to the changing tectonic nature of the area, and it gives us this state of flux in the landscape. Further north along the San Andreas is the town of Parkfield, California, which is sometimes called the earthquake capital of the United States. We're going to fly to a particular place in Parkfield. It's at a rather ordinary bridge overpass over a stream. And we're going to go down to street level because we're actually going to get welcomed to the two different connecting plates, the North American plate and the Pacific plate. And we can see here on one side is a sign for the North American plate. You are now entering the North American plate. And on the other side is you are now entering the Pacific plate. What's interesting about this bridge is that when you look at it from one end, you can actually see that the railings are not perfectly straight. If you look really carefully on that side, yeah, that arrow there, you can see that the railings are shifted off to the right in the picture. And we're looking at, on the far side of the bridge is the Pacific plate side, and the Pacific plate is moving to the northwest. And that would be the right in the picture. And so, yeah, so even over the short time this bridge has been constructed, it's been offset enough. Now, the engineers, state and county engineers probably check this bridge to make sure that it's safe to drive over, but well, I sure hope so that they do. But that's what makes Parkfield an interesting place tectonically, and that the fact that the earthquakes along the San Andreas frequency here is so consistent that the U.S. Geological Survey have set up a great amount of equipment monitoring in this area along the San Andreas. And we can actually watch local video of the 2004 earthquake of this area. One of the reasons some parts of the San Andreas have more violent earthquakes and some fewer earthquakes really has to do with the rock type along the fault. Some parts of the rock, some of the rocks along the fault may be more crystalline or igneous rocks. They've built some of the areas along the fault where they've poured bedrock, and so they've done that plenty of pours along the Parkfield, California section of the fault. They encounter the mineral talc. Now, talc is a mineral that's very soft and actually very greasy feeling, and it absorbs water. And that may explain why some areas of the fault have much more frequent earthquakes that allows the fault to slip and slide a little bit more easily, as opposed to places where there may be more crystalline rock that does not contain minerals that have that ability to absorb water or have those soft minerals to allow this to reduce the friction along the two sides of the fault. So our next stop along the San Andreas is a little bit north of Parkfield. We're going to stop at real quick to the Crystal Springs Reservoir, and just to the north of that, the San Andreas Reservoir. You can see there are long linear lakes. Now, these are artificial lakes. They were made much larger by humans, but they were originally lakes for wetland bog areas to begin with. Because we are right on the fault, the rocks along the fault, they're grinding past one another. The rocks get ground down into rock powder or rock flour. That rock flour often prevents groundwater or rainwater to percolate through. And so sometimes it may stay at the surface and cause what we call a sag pond. Now, I said earlier that area along the fault might be lower elevation or depressed area to begin with, right along the fault. And if it's collecting water because the ground up rock, the rock powder, is preventing percolation, infiltration into the aquifer below, it stays on the surface. And so you can often spot the San Andreas in these dry areas by the abundance of vegetation, often in a linear form. And when you're hiking along the San Andreas Trail, south of San Francisco and just in this area, often where you have abundant vegetation, you know you're right on the fault because the groundwater stays close to the surface because it doesn't infiltrate deeper, because the water is held close to the surface because of the rock flour that has been ground by the rocks, grinding the frictional grinding of the rocks at the surface along the trace of the fault. And so Crystal Springs, humans took advantage of these sag ponds and created artificial reservoirs. And here we have the two long linear reservoirs, Crystal Springs and San Andreas. And now we're going to move further north, just to the south of San Francisco, or right outside of San Francisco, to a place called Muscle Rock, which is just south of San Francisco and was actually the closest point to the epicenter of the great 1906 San Francisco earthquake. And it's actually where the first time where the San Andreas Fault enters the San Francisco Peninsula from the northwest and moves out into water for the first time. Muscle Rock and this whole area is what we call a horse. Geologists have all sorts of interesting names for features, but a horse is actually the name for a rock that gets caught between the two sides of the fault. And what we have here is rock that got caught in between the Pacific plate and the North American plate. And when we look at this area of Muscle Rock and along the coastline, you can actually kind of see, it's a little bit weathered, but you can actually see dark rocks on the bottom here on the cliffside. And you can also see this on Muscle Rock proper. Dark rocks overlain by lighter rocks. And that's actually the two plates interacting with each other, the two sides of the plate. So we actually see it from the two different types of rocks that are in contact with each other, one on the bottom and one on the top. And so they are from very different places on our planet. This is, the Pacific plate has been steadily moving to the northwest, and that's what this is the result. These different rocks of different ages in contact with each other, different types of rock from different ages in contact with each other from very different places on our planet and very different origins. And our last stop along our San Andreas tour is going to be at Tamales Bay. So we're going to leave Muscle Rock and we're going to fly past the great city of San Francisco, and say hi to the Golden Gate Bridge. I strongly suggest you put that on your bucket list.
And now we're going to finish this tour by flying northwest to Tamales Bay, which is the home of Point Reyes National Seashore. Tamales Bay is also a long linear depression, kind of a sag pond, and it's now a bay, and it's the trend of the San Andreas Fault itself. The rocks are completely different on both sides of Tamales Bay. The Pacific Plate side here, the western side, is all granite. It used to be magma at one time. It's Cretaceous in age, so the dinosaurs were still around when this rock was magma and turning into rock. The North American side, it's a little older. It's older Cretaceous. It's into the Jurassic time. These are slightly metamorphosed sedimentary rock. There's some sandstones and shales, conglomerates. There are some fossils there. It's called the Franciscan Complex. All waterborne rocks, all oceanic in nature. So very different rocks on both sides of the fault. Different origin, different age, and they were brought here by the San Andreas Fault. And then we just continue with the San Andreas. It continues past Bodega Bay, which, little note, where the great Alfred Hitchcock film The Birds took place. The fault continues out to Cape Mendocino and the oceanic fracture that makes the San Andreas Fault terminate there. And that is our San Andreas Fault. Hope you enjoyed it.